Hi everyone, my name is Priyanka Singh and I'm a postdoctoral fellow at the Observatory of Trieste, Italy. In this video, I'll present some of the key highlights from our recently published paper on Precipitation-Limited hot halos done in collaboration with Mark White and Biman Nath. So there has been a lot of hot debate on what's CGM and what's ICM. For me, when I use the word CGM, I'm referring to the gaseous reservoir in galaxies with virial masses smaller than 10 to the power 13 or so. On the other mass end, we have clusters with their ICM, and in between, there are groups with their intragroup medium. The motivation behind this work is to explore the prevalence of the so-called precipitation limit from massive galaxies to galaxy clusters, and the tools we use are Sunyaev-Zel'dovich effect and X-ray emission. One of the key ingredients of this precipitation-limited model is the ratio of gas cooling time to freefall time. And in this framework, this ratio is kept above a critical value. And whenever it falls below this value, a loop follows, which brings it above this critical value. There has been a lot of observational evidence that that this critical value is around 10 or so. In this work, we have used the stacked SZ measurements by Planck collaboration and stacked X-ray measurements by Anderson et al. And the two data sets span 2 orders of magnitude in mass, thus providing us the estimates from CGM to ICM. So given the data, given the model, we perform MCMC analysis to put some meaningful constraints on our model parameters. And we find that the value of this ratio varies from 50 to 100, depending on the pressure profile extrapolation. This extrapolation is required to estimate the SD signal coming from a much larger size than the size of the actual galaxy because of the poor resolution of Planck. And that's also the largest source of unsystematic uncertainty in our modeling. So here is the key figure from the paper showing the observed density profile from galaxy clusters to groups to down to Milky Way mass scales, comparing with our best fitting predictions shown by the red and blue lines in all these panels. And as it's clearly visible from this figure that our model prediction in most of the cases lie below the observations. And this discrepancy between the results from the stacked measurements and individual profiles cannot be explained by Eddington bias alone. Another key feature are these gray lines in all these panels. And these gray lines correspond to the value of this ratio equals 10. And they very nicely provide an upper envelope for the density profile in all these cases, thus further indicating that all these systems spanning to more than 2 orders of magnitude in helium mass obey the precipitation limit. To summarize, we have presented a really simple analytical precipitation limited model, which is tuned to fit the stacks of integrated SD and X-ray datasets, spanning uniquely 2 orders of magnitude in helium mass. Having said that, yes, there are some limitations, and one of them is our model overpredicts the X-ray luminosity at intermediate halo masses, even though it performs well at CGM and ICM scales, indicating that the model is probably too simplistic to capture powerful feedback at these intermediate mass scales, and we believe that there is a scope of improvement there. With that, thanks a lot for your attention. The link to this paper is available in the description box, and feel free to drop me an email or contact me on Slack if you have any questions or comments. Thank you.